Welcome back to linear algebra. In this video, we're going to be talking about the dimension of a vector space. Last time, we were looking at the idea of a basis, and we saw that there are several different bases for any given vector space. Earlier, when we started talking about abstract vector spaces, I mentioned that we were only going to deal with finite dimensional vector spaces in this course. There are vector spaces that are infinite dimensional, and they have a lot of incredibly useful properties. They're just a little bit beyond the scope of a course in algebra. But today we are finally going to get to the point of determining how to find the dimension of a vector space. It turns out that it's tied perfectly to the idea of the basis of a vector space. Every basis for a particular vector space has the same number of vectors. This is not quite strong enough to call a fundamental theorem, but it is incredibly close to a fundamental theorem of linear algebra. There's another theorem coming that's a little bit more powerful than this. But this is kind of the lemma to that theorem. As is often the case with a fundamental theorem, actually proving the theorem is a little bit beyond what I want to get into this semester. I do want to mention that in the textbook, they do walk through the proof of this theorem by way of a couple of other theorems. So if you're interested in taking a look at why this is the case, I invite you to do so. But with a little bit more vocabulary, if we let V be a vector space and we pick any one basis, we will call the dimension of V the cardinality of that basis. Remember from set theory, the absolute value bars in this case, because B is a set, is read as the cardinality, and it is the number of vectors. And because of our theorem, every basis has the same number of vectors, so no matter which basis we pick, the cardinality will be the same, which means that this is a well-defined value, the dimension of V. And we're going to use dimension for a number of different things throughout the semester. But the first place where I want to use it is to show you what we need to actually prove that theorem. Right? This is This theorem tends to kind of loop in on itself, which is part of why I said it's a little bit beyond what I want to look at this semester. But the lemma to the theorem is actually kind of interesting on its own. Remember that a lemma is a theorem that is technically dense, but incredibly powerful and useful for proving that a theorem is true. Let's let V be a vector space with the dimension of V equal to n. And let S be a subset of V. If the cardinality of S is greater than n, then S is not linearly independent. If the cardinality of S is less than n, then the span of S is not the entire vector space. The lemma here is the tricky part of the theorem. I hope that you can see from this lemma how to prove the original theorem. In order to have a basis for a vector space, it must be linearly independent and it must span the vector space. So if we know one basis and we know its cardinality, we know that another basis can't have a larger cardinality or the other basis wouldn't be linearly independent. We know that the other basis can't have a smaller cardinality because then the span wouldn't give you the entire vector space. So Goldilocks says that every vector space, or every basis for this particular vector space, must have a cardinality of n. Very circular in how we have to talk about it, but the ideas hopefully mostly make sense from there. We saw in the last video that the Euclidean vector space R to the n had a basis of n vectors, the standard basis, 1, 0s, 0, 1, 0, 0, etc., all the way through to the last one, 0, 0, 0 to n at the last entry. Because the basis of Rn has n elements in it, the dimension of Rn is n. Likewise, the dimension of the polynomials of degree n. If you go back and count, the standard basis for polynomials of degree n was 1, x, x squared, all the way through to x to the n. If we think about that 1 as being x to the 0 power, I think it becomes clear that Pn has, or the basis of Pn has n plus 1 vectors in it. So Pn is an n plus 1 dimensional vector space. There's really not a lot to dimension for right now. Once you understand how to find a basis for a vector space, you can count the number of vectors in that basis and use that to determine the dimension. Before we wrap up here, I want to mention two other theorems on the basis or on the dimension of a vector space. In order to show that a set is a basis, we had to establish that it is linearly independent, that it spans the vector space. If we know that the cardinality of our set is the dimension of the vector space, then either one of those will imply the other. If you know the dimension of your vector space, and you know that you have a set which has the number of vectors in that, or the number of vectors that a basis should have has a number of vectors equal to the dimension, then being linear independent is enough to determine that you have a span, and having a span is enough to determine that you are linearly independent. Once again, that's not a theorem that I'm going to prove, but that's something that can be incredibly useful to you as you move onward in the course. With this, we have kind of all of the tools that we need to start talking about vector spaces and how they relate to each other. In the upcoming videos, I'm going to start combining these ideas. We are now going to be able to talk about a vector space in terms of its basis. We're going to be able to move our representation from one basis to another basis in order to get a different way of thinking about vectors. And we're going to be able to generate bases for a vector space, knowing things about the dimension. So some things to look forward to. But for now, take a look at the practice problems on dimension of a vector space, and I'll see you next time.